So let's dig into rolling motion mathematically. So this is where all the things adds up. Now, first step is to express, we get an expression for linear displacement of center of mass in terms of angular displacement and linear speed of center of mass in terms of omega. So let me put it across to you guys in this way. I have a wheel, right? That's the center and it has moved forward. Okay. So it has moved forward from here till here, around this length. So I'm going to highlight that length. Remember, the wheel is rotating. So something like this, I guess, to this extent. That would cover up the length, right? Yeah. That amount of rotation leads to this displacement. Do you guys agree? So basically, the wheel has rotated and it has moved forward, direction of motion. Okay, now, so to complete this, we have this and this, and say this radius is r, and the angle over here is theta. Now, this length from point A to point B, this length is, say, small s. The radius is r and theta is in radians. And we have s is equal to r into theta. Simple, straightforward, linear displacement. So basically, this length is what the center of mass has got displaced. Can you see that? Center of mass has moved from point A to point B. This is AB. This length to this displacement to will be AB. Okay. So basically, a pure rolling motion of a cylinder. Let me write it in terms of, consider a pure rolling motion of a cylinder, or whatever you guys want to call it as, of radius r. So this is nothing but your rolling. Till now I have not officially defined rolling. I'll be doing that in the next video. So it's nothing but rolling without slipping. So we'll dig into the statement a bit more actually. So this being the case, when the cylinder rotates for an angle of theta, then center of masses linear displacement is given by small s is equal to capital R into theta. From this, we'll be able to expand to the idea of linear speed of center of mass. This will be ds by dt, center of mass. This will be r d theta by dt, right? R is constant. D theta by dt is what can change what's happening actually. And that will be nothing but your omega. Agree? So with this as our fundamental grip on center of mass and its movement and the velocity and stuff, let's move on to the effective velocity of a point in general in a given rolling object. So let me put a ground first. So that's our ground. The object is moving on this. Okay. And then This is where the point of contact is on the ground, and let me draw a vertical line. So through this is our center of mass passing. And somewhere around here is where our center is. Okay. Now we have point P. And we have point, say, C or O. We kept calling it as, this I'll call it as B, and this I'll call it as A. Again, we can call it with any name, not an issue. So we're considering a point P. And everything is we are going to discuss in terms of point B, the ground basically. So all the discussion will be with respect to this in relation to this, not actually in relation to that, in terms of this, sorry, that's what I meant, sorry, in terms of the velocity at the center of mass. Again, I'll repeat, we are discussing everything with respect to this, in terms of this, in terms of that. That's the whole thing. Okay, so let's come back. So we are looking at, first thing is, what is the velocity at point P? What will be the velocity at point P? It's combination of two things. One is the linear motion, right? So the linear motion would be same as that of the velocity of center of mass, is it not? So I hope you guys remember this video. So all the points, remember, yeah, again, this goes back to the previous video discussion. Everything, all of the rolling thing are divided into two parts. One is your translation motion and other is your rolling motion. So first we are looking at the translation motion. So with respect to translation motion, the object is moving forward with the same velocity as that of the velocity of center of mass, right? R omega basically. Okay. So this will have a velocity of v com. Next, the rolling motion. So rolling motion would be with respect to the center, it would be perpendicular and it would be in that direction basically. So this will be v, okay, rolling, R-O, not T, sorry, R-O-L. That would be your velocity because of rolling. As a resultant, how should I go about finding the resultant? I can use triangle law of vector addition. If not, I can use parallel law of vector addition. So all I have to do is draw a parallel. So something like that. Okay, so I can cut and shift it over here. And if I've done a good job, then if I join this, yeah, that's our parallelogram. So our resultant vector would be here, this direction. That's the velocity at point P. Again, let me slow down a bit. Let me actually change the color also. So let me change this to, yeah, that would be better. And this is related to this actually. Again, this is because of pure rolling. So guys, let me go back to the starting video. So when we started with rolling motion, that is just the previous video, we decided that we can't look at pure rolling, or sorry, rolling motion just as rolling motion. It's kind of complex. So what we are doing here is we are dividing it into translation and rotation. And when it comes to translational motion, So we have the velocity at point P, any random point. It need not be here. It can be here, here, here. It could be anywhere. I'm taking one point P. The thing is, we are trying to express the velocity at point P. One is your translation motion. Translation motion at point P, if the object was not rotating, it's not rolling at all, it was just going right. It's sliding basically. The velocity of any random point on the circle will be within the circle on the circle will be same as that of the center of mass. It'll just keep going with the same velocity as that of center of mass. So I wrote it as v com to the right. But when it comes to rolling motion, this has to come from your second, third chapter. You guys have to remember this. It is perpendicular over here. So I'm just going to do it a bit light. You guys can't see that, I guess. Right, this will be perpendicular. And this line is coming from the center. And that will give me my velocity because of rolling. Of course, there are certain values to this. I'm not talking about the value. I just took randomly the vector. And as a resultant, I found out Vp through parallel of vector addition. That's all. This is the diagram. Okay. So it's important for us to understand the diagram. So with that understanding, let's move on to the effective velocity at point P. Okay, a random point actually on the object. So it can be explained. It can be explained or understood as a combination of translational and rotational velocity. Okay, so first we'll start off with, I hope I don't have much space. Resulting velocity at different point. Okay, I'll try to fit in translational velocity, or I'll directly go, guys. I don't have space, or I can do it over here also. Chalo, I'll do it here. Vt is equal to same as V center of mass, and that is R omega. Okay. Then we have, because of rotational will be VRO. Oh yeah, it's T only. Okay, rotational ROT will be equal to R, capital R, omega. Oh no, small r. So this would be small r being over here. Okay, point P is at random radius r. So distance, this is where, actually I need to write this, where the small r is distance of P from center of mass. Okay, guys. So I'll call this as 2. Now, resulting vector at different point would be what? So basically, the V effective at point P will be nothing but vector addition of those two. That's what we did. I'll call it as TR. I'll call this as TR, translation. It's a vector sum of those two. So in terms of magnitude, what will it be? In terms of magnitude, it would be, if I substitute them, this would be R omega square plus R omega the whole square plus small r omega the whole square plus, I hope you guys remember this, 2 r omega square sine of theta. Is this correct? There are two mistakes. What are those? One is the root. What is the other one? Yes, this should be cos of theta. Okay. And the angle. So this is your direction part. Sorry, magnitude part. The direction part. Direction of your resulting vector, resulting velocity. So this would be, it will be, or let me change the color. It will be actually perpendicular to the line. It will be perpendicular to the line joining points B and P. Okay, point B is this. It would be always perpendicular to this. Okay, so that would be your directional part. Okay, so almost there. We are trying to understand that blurry wheel. So for that, I need to take up this again. And let's consider the point B. And say the point P is over here. Now, we have seen this actually. So at point at the top, how would the angles be? Both of them, your translation motion, obviously the translation motion will be to the right. The rotational motion, since the center is over here, right, it has to be perpendicular, so they will add up. What I mean is this point P, if it's over here, both of them will be pointing into the same direction, so they will add. Okay, they will add. So your VT plus VROT. This is VR if I'm right. This is rotational motion plus translation motion. They will add up. The result will look something like this. At the center, you know that there's no rotation, so it's only the translation motion. Say it would be just because of translation motion. And at the bottom, it's the difference between rotational stuff and translational stuff. So this is VTR minus, it would be so, it's the difference between them. Now, let's talk about different points. Let's talk about, let me take up different points. So this is point A, that's point B. Say this is point M, this is point O, this is point, say, N. Okay, so with this as the center, right, point M is at distance of, say, R by 2. So this would be at the distance of R by 2, and this is at the bottom at the distance of R by 2. Okay, so this is a scenario. So I'm trying to figure out what is the velocity at all of these different points, starting from B, N, O, M, A. We have a basic idea of A, B, and O. M and N are new points. So we'll make use of this formula and figure it out. Okay, so let's do that. So velocity effective at point A. Let's start with that. So we have R square, omega square. Here R is, small r is capital R, right? Or let me do it systematically. The first one I'll do a bit systematically. So here, the small r is capital R, right? The small r is nothing but the distance from the Small r is distance from the center to the point P. In this case, the point P is shifted to, remember point P is random point. Point P is shifted to point A. So the distance from point A to O is r, radius, right? And then we have theta. Oh yeah, sorry, I didn't define theta for you guys. Theta would be over here. Just a second, let me zoom in. Okay, where is it? It's bottom. So this is your theta, right, guys? Angle between the vectors. So I'll write it over here. Don't get confused. It's not, it's between the vectors. It's not the resultant vector. It's not related to resultant vector. At least not, sorry, not directly. I should be zooming out. So theta here is how much? Theta is the angle between V com and V rotation. How much will that be? It is both are pointing to the right. So theta here is 0. Okay. This has to be very clear. And now I'll write the result directly. So r omega square plus 2 r square omega square cos 0 is 1. So 2 plus 2 is 4 and root of 4 is 2 r omega. Yeah, r omega. Okay, so what is r omega? R omega is nothing but your velocity of center of mass. The translation velocity of center of mass. Right? So that is translation, and this is your rotation of point P. Actually, that was right. They are equal. Sorry, my bad. Nothing. Please don't get confused. So it's equal to velocity of center of mass. So I can rewrite this as it's 2 times the velocity of center of mass. Do you guys agree? I didn't do anything fancy over here. I just substituted the values to this. All you have to understand is why is theta 0 and r is capital R, that you guys can understand. Why is theta 0 is something that you need to know. Because both will be pointing to the right. Both will be pointing to the right. Now, half the way. So half the way, what will it be? Or we can go with point O. Point O, it's quite simple. It's just V com. And here at the bottom, I'll go with the bottom. That's also very simple. V effective, let me change the color. V effective at point P. Here R is minus R and theta is equal to 180 degree. Taking it as plus R. It's the distance. So it's just R and theta is 180, and we have here V effective at point P is equal to root of R square omega square. So there's a bit of math over here. That's why I'm writing this. Plus R square omega square plus 2R square omega square cos of 180. And cos 180 is root. And cos 180 is minus 1. And so this 2 will add up to 2R square omega square, and this entire thing will cancel each other out, and this is 0. And this value will be 0 meter per second. And this value is 2V com. So let's take up point M. Again, I'm trying to adjust everything in a very tiny space. V effective at point M. So here in this case R is R by 2, half the distance, right? And theta is 0. And so here the V effective at point M will be equal to R square omega square. This is not going to change. And this will be R square by 4 omega square, right? Plus 2R square by 2 omega square cos of 0. So that's 1. So this and this will get cancelled. And we have 2. 1 by 4. 2 and 1 by 4 will be, okay, 2, 1 by 4. 2 1/4 basically, 9 by 4, right? 9 by 4 is nothing but 3 by 2 root. And we have r omega. So this is nothing but 1.5 times the velocity of center of mass. Can you see that? It's 1.5 times the velocity of center of mass. So if I keep doing this, so finally we have V effective at point N. That's the point which is below, below O, point N, half the way. Can you see the values, what is happening to them? This is r by 2, but theta here is 180 degree. So as and when you calculate it, we will see one calculate it and plot it as well. We'll see something unique. So all of this is r square omega square plus r square by 4 omega square. All of this will remain the same, but this will change. This will be minus r square omega square 0.4. So basically this is nothing but this and this will get cancelled. This is half of, right? 1 by 4 root is half, that is 0.5 times of velocity of center of mass. So basically if I plot it, okay, I'll do a rough work. If I plot it, so this is going to be 0. This is double of the velocity of center of mass. If I join this case, this will help me now. I'll tell you why. If I join this, oh, let me not use that. Let me use this. If I join this, right, this is what will happen now. So this would be around the center. This will be your VCOM. Here would be 1.5 times the length of VCOM. This would be half of VCOM and this will be 0. This is half the velocity of center of mass and this is your double the velocity of center of mass. This would be the picture. That would be your point A. This is point actually O. This is point B. This is point M and that's point N. This would be the picture. And if we go back to the photo, can you see that? Can you see the values over here? This is 0. This is the velocity of the center of mass. It would be double. The top will be double. Middle will be 1.5 times. At the bottom, between the bottom and the center of mass, somewhere over here, it's half the value. Half the value of whatever this is. If this is 10 meter per second, this will be 20. This will be 15. This will be 5 and this is 0. Can you see that? And so the blurriness. See, the math is able to explain this. And it was a simple math. And you guys did it, you know. Yes, I mean, I helped around, but end of it, if you understood it, it's because of you have understood it. Nothing else. Okay, so yeah, basically this is it. See how easy it is. Okay. So that's how you'll be able to explain such complicated stuff. So again, I'll go back. Rolling motion is complicated. If you just try to understand it, dive into it directly. But if I use translation plus rotation, it makes it simple. So everything is expressed in terms of your center of mass. For that, I need to get expression for center of mass, which I did over here. Now, once that happens, I can take a random point on the circle, within the circle or the wheel, and derive out a velocity, expression for velocity. Again, here too, I am breaking it down to translation and rotation and expressing in terms of center of mass. And effectively, I get this as your effective velocity, the resultant velocity. So with that in my hand, I'll be able to move on to finding values at different points. It's just a matter of substitution of theta and r and end up with such beautiful set of values, which when I plot is able to explain the blurry photo that we happen to see. Okay, and this is not with that wheel itself, any pure rotational motion, any kind of pure rotational motion of anything, right? Circular stuff I'm talking about will show such behavior. Other structures also, but anyways, let me not get distracted. Point is, you will get to see this. I hope you guys are, under that impression, the wow factor is there in you guys. You are able to feel that. Because when I saw that, and it is a wow factor. When I saw that all of this for the first time, and such simple maths is able to explain this, it's quite impressive, honestly. I hope you guys are enjoying this. This is where all of the things that you have learned is coming together.